extra strong Roman concrete,
fully hydraulic,
structural molded connections,
It's the
structural
engineering podcast.
Welcome to this week's episode of the Structural Engineering Podcast. My name is not Zach.
And my name is Zach.
So this must be the Structural Engineering Podcast. This week's episode we're calling, I got a long title here, I'm pulling this quote, I like this very much. This is from 1828 by a guy named Tredgold, and this is the title of this podcast. Girders should always be made as deep as they can to avoid the inconvenience of not being able to move on the floor without shaking everything in the room.
I like it. On another note, probably called floor vibrations.
In summary, yeah.
In summary.
Subscript, floor
Yeah.
vibrations. But before we do floor vibrations, like always, we do the news.
We do part of the news.
We do a little bit.
We do a little. We just tickle the news. So for this last week, two big things kind of has come up. One being Denver International Airport, and the other is some seismic retrofitting in California for soft stories. So to start off with the Denver International Airport, they're currently working on expansion of it, and the main terminal, they went in to do some work, and they needed to support equipment off the main level. So prior to doing that, they took some cores of the concrete that was there, and they found that it broke at a significantly lower than the specified design. So they're currently working through what that means. I think it's just kind of interesting. It's been there for 25 years, and it's still not breaking at the specified strength. They're talking about how they're going to mitigate that issue. There might be with shoring or something like that to be able to get the crane in there that they want to use, or they might do smaller pieces.
And they didn't say what was breaking it, right?
No.
They just said it was under. Yeah, I'd be
They just
curious
said
to
it was
know.
under.
And what it was designed for. Just a regular old slab meant for people, so probably
I think
4,000.
Yeah.
I mean,
they had
older
fairly high
slabs could be-
loads.
Oh, really? Okay.
Yeah, I think it said something about 250 was what that floor was designed for. Whether that was, I'm not sure what the floor is made up of.
Yeah.
I believe it's a composite structure. I don't know how deep the floor is there. On this week's topic question, you've been to that airport a few times. Have you ever felt a little vibration in that floor?
No.
Yeah, I'm there with you. It feels very solid. It's a very solid floor.
Good. Checks out. And then part two of the news, so this California mandate, this is Pasadena, California. They are getting closer to issuing an ordinance that would require the owners of about 500 soft-story homes to seismically retrofit their homes. So that would be going down and making sure that the lower level is not weaker than the upper levels, which would make it collapse a little more likely.
Right, I think the most common houses there that have that is where it has the first level parking. Mm-hmm. So usually it's wide open on one face or two faces, and then there's just like a column sitting there.
Yeah.
Makes it super weak, and a lot of the earthquakes they've had there, those have just collapsed.
Yeah.
Due to that weak story. Yeah, there's a lot of counties and cities in California that have already done this. So not something necessarily completely new to California.
But it's kind of a lot to ask. I mean, 500 homes, multifamily homes, they're saying anything over 2 stories or 2 stories and over, and 4 families and above.
Yeah.
And that'll make sense.
Yeah, I believe they're looking to get some funding through the government, I believe, to help subsidize some of that cost. But it is quite a cost to the house owner. Take your building up to current code or to 41 levels or whatever. A lot of companies spent a good chunk of change retrofitting.
Oh, I bet.
So, I don't know, there's a lot of contractors and engineers in California right now that are kind of doing that. And so it'll be interesting to see if they'll just move into that area or what. So.
I bet they will.
All right, so that closes
Yeah.
out our news for this week's podcast.
Now let's shake things up.
Ooh,
I feel like there's a tremendous amount of puns that could be placed in this one.
this is going to be a very
It's too
punny
easy.
podcast, potentially.
Yeah, we're talking floor vibrations.
Yeah, why don't we dive into a little chat about that?
So the idea of floor vibrations being a problem has been around for a really long time. The quote I read, to open this is from 1828. I don't know who Tredgold is, but he already knew that floor vibrations were bad. It seems like the tolerance at the time. I mean, he's saying everything in the room shouldn't shake. I think we've gone beyond that as far as what we call acceptable vibrations. I think people would be pretty nervous if everything in the room shook from walking.
You said 18.
1828.
Yeah. Which, yeah, that makes sense.
Yeah, there's less shaking going on now, which is nice. But the deflection criteria we have right now in place is there's a lot of reasons behind it. There's serviceability concerns, cracking, comfort, but then this also kind of helps mitigate this deflection problem. So a span of L over 360, it helps to control that floor vibrations.
I think is a huge issue in a lot of buildings, especially for new tenants that are coming in and don't know what's going on.
Yeah. One thing I heard while we were reading through some stuff is sort of an old-timey claim is that when we switched, or as we're switching from ASD to LRFD, that's when you started to see more floor vibrations. I don't think that's necessarily. I mean, there's a little bit to that. So all these things happen at the same time. There was an increase in our steel strength. So, beams, columns, a lot of things used to be grade 36, and now they're more or less all grade 50 steel for wide flanges. So right at the same time, computers came about, right? So not only is that fun because we can analyze these things, but on the same side, offices got a lot lighter. We're used to hold papers and heavy desks. There's a lot of damping and a lot of weight in there, which really helps negate the effects of vibrations. When we have an office that's mostly made up of computers, it's super light. So we've got lighter structure, longer spans, less damping in an office, and all those things kind of combine to make this more of an issue. I saw a couple things of like old offices that were retrofit, and when they were some office filled with file drawers and like tons of people packed into cubicles, nobody ever noticed vibrations. But as soon as they opened up the space, filled it with small computers instead of paper everywhere, then vibrations were a big deal.
What are the big considerations when trying to figure out your vibrations in your floor system? What are the drivers?
Well, there's kind of a pre and post here, right? So you might get a call that says, hey, I found this floor and it's vibrating, what can we do? Or hopefully you look at this before you do the design. Isn't always done. Smaller structures, if you're not running something in one of these software programs, if you're running a beam in Intercalc, some small system, you're not going to know if this thing's going to vibrate. A typical composite or steel frame structure with a concrete deck vibrates around 4 to 8 hertz. So that has the potential to be a problem no matter what. A person walks roughly around that 2 hertz range, so they're putting a force into that, and as long as you're in a multiplier of the harmonic, you can excite this beam. So if you have like a sort of flexible floor at 4 hertz, and you have someone walking at 2, you can put that structure into resonance. Thing is, if the acceleration is slow enough, you just won't even feel it. So I kind of dove out of that question a little bit.
Let's say I'm a new engineer.
Yeah.
New to designing all this stuff. What do I do? What am I looking for? You're talking hertz and accelerations and this vibration thing.
Yeah.
I never learned that in school. It was never discussed. I mean, what would be a good things to look at to help mitigate this issue?
Yeah, that's a good question. So, in design, if you're using a software that is a little more involved, something like Arisa or a RAM, there's built-in components in that software that will tell you the acceleration and the frequency of the floor system that you're putting together. So if you're doing something that sort of warrants this sort of design, which can be something where there are sensitive occupants, maybe there's a gym, or reading these papers, they use the word aerobic more than I've ever seen it used in my life. It seems like there are aerobic facilities everywhere, hidden in buildings.
Yep.
But apparently, if you had an aerobic facility next to an office, you would really want to know that those vibrations were transferring over. So those are some situations where it's much more important to take a dive into. Also, what's really important here is what makes up this vibration, basically. Like, what are you looking for? The natural frequency is proportional to the square root of the stiffness of this member and the mass of the member. So if you have a floor system and you have a beam spanning across, if you're just looking at single mode, one beam, not sort of a system here, it would be a pretty easy calculation. It is, what is the stiffness of that member? The more mass you add to that, the higher the frequency goes. The lower the frequency. The more stiffness, the higher the frequency. You can play with those values to get yourself out of that problematic range of frequency or acceleration.
If I'm looking at this, the big things I need to look for is I need to have mass and I need to have stiffness.
Yep.
That's my good starting point.
That's your good. Those are the tools you have.
That's the 101.
That's
Those
the
are the two
101.
things I can fix. Now, what about my fixities of my beams, my elements?
So that goes to the stiffness. If you have a higher fixity, you have a higher stiffness in your beam. So if it looks like you're having some issues, that's a great way to mitigate this potentially. Not everything works, and the more I read up on this, buildings can be so complex that it can be really hard to nail down a perfect fix every time. The AISC has a great podcast on this, and even these experts in the field said, they have a pretty good idea. They try something. They don't, put the drywall back up till they know it's working, because they might have to try something else. A lot of this is sensitivity, and different people have, different sensitivity to vibrations, which is super important.
The things you've been talking about, I'm sure you're going to jump into design guides, and vibrations are, is what you're saying, not thoroughly understood to a level of which everyone feels comfortable with those vibrations.
Public perception, you think. Yeah, I mean, definitely when you get high vibrations, people might think the building is falling down. It would be the worst case, right?
Right.
In different situations, you would tolerate much stronger vibrations. So Design Guide 11, put out by ASC, vibrations of steel frame structural systems due to human activity.
Which is the holy book of vibrations.
Yeah, this is what you got. I mean, this is...
For more than just steel material. So they only discuss steel, but the amount of testing they've done has developed where human comfort is and what type of structures
you can extend that into a lot of other stuff, certainly. Sort of the parameters laid out in this. But going back to, human comfort levels, someone's sitting in an office, they've decided that you can tolerate an acceleration less than 0.5% of gravity. So anything above that, you would be disturbed in some way. Going all the way to the other range, if you're doing aerobics, like everyone seems to be doing in these books, you can tolerate 10% of gravity, because you just wouldn't feel it, right? That's what this is. You're sitting perfectly still in an office, just staring at a computer, thinking about your life. You could feel 0.5% of gravity, but yeah, you're dancing.
Yeah, you probably wouldn't notice it until the floor came up and hit you before you expected it.
Yeah.
Oh, well.
So, and there's a whole spectrum of that, and the Design Guide kind of lays out some other parameters. I think, for normal commercial use, you're at 1.5% of gravity is sort of the tolerable. You're walking around, not necessarily sitting perfectly still.
It's like a retail.
Yeah, retail situation. So depending on, the use, you can get away with a lot of other things. And so also in that, depending on what you're doing in the space, there are different forcing functions. So if you're looking at an office, you're mostly considering sort of footstep action, right? Mm-hmm. So a person walks around, they walk at a frequency range of between 1.5 and 2.5 hertz. You can kind of picture that, right? As you take a step, if you one Mississippi it, you get about 2 in that motion. So that is sort of the frequency range that you're considering when you're looking at that situation. When you're doing these aerobics or normal jumping, as the Design Guide says, you're closer to 2 to 2.75. So since you're in this multiplier situation, now you're going up to 5.5, and you're still in one of those very lower modes. And it's the lower modes are the ones that are you get the most amplitude, most acceleration. So if you're exciting, what would be the third mode or something? Yeah, it's just you're not really going to feel it the same way there. It's much smaller amplitude.
Design Guide 11 is the basis of all designs. It was a good starting point, I should say, of all good designs. Kind of understand what vibrations are now. I have some words, accelerations, hertz. To me, the next thing would be to understand what the criteria should be for the structure I'm working on, right? Now, where does that conversation come in play?
So you're talking with the client here, when do you bring this up? I think, for anything multi-story, that needs to be brought up immediately. There's sort of a baseline that structural engineers should be designing to, no matter what. I mean, you know the occupancy of the building, right? And it's probably best if you can to just design to that 0.5% of gravity. That way, no matter what the occupancy ends up being, if someone is sitting still, you're not going to feel this.
Here's a good question.
Yeah.
Where in the code does it say I need to do this?
I think vibrations is one of the weird middle grounds where it's not specifically codified. Now deflection limits are, but the vibration frequency is not something that explicitly is said, I don't believe. So it's more of a comfort and performance sort of level or criteria.
Okay, so you'd want to have that conversation with your client then. make sure that you're designing to the right level of what they're expecting.
Absolutely.
And maybe they're not even expecting one. They're just wanting you to meet live load deflection criteria and call it good.
Yeah, but at the same, point, it's worth educating the client on what is, why you might want a higher deflection tolerance, or why it might look like you're oversizing a beam. Mention the idea of this, vibration criteria that you're trying to meet.
Because potentially you're adding cost. You're adding significant costs.
Yeah, I mean, in long spans, it could be the case of really increasing your beam depth or weight to meet a certain vibration tolerance. If this is a hospital setting or something, vibrations are way less tolerated, especially in a surgery arena, or really just any equipment. So it's important to let the client know up front that designing for vibrations might mean higher cost in certain situations. Maybe it's worth shortening your base spans in certain areas.
Yeah. Okay, so you said we also have vibrations from equipment?
Yeah, so a human can force vibrations on a structure at that 2 hertz level, like we talked about. Equipment can be just about anything. So if we're looking at an MRI machine, now I don't know, we've done only one of these. I don't remember if it gave a frequency that it operated at. There's not really the same sort of moving parts in MRI as there is in a HVAC unit or rooftop style thing. But yeah, some equipment will give parameters that it operates under, usually in a hertz, and it's usually fairly high. This is higher than 2, higher than 10. This is like 30 to 50 range.
So what sort of structure would land in that range?
So, a wood structure or something like cold form, something that's really stiff and shorter spans, that is maybe 10, topping out around 30 hertz. Thing is, people can't really feel beyond 15 hertz very well. If you have your hand, I think guardrail is a good example here. So we were looking at a guardrail the other day, and if you give it a smack and put a sensor on it, this guardrail outside our office, or handrail rather, vibrates at 30 hertz. You can definitely feel that. But if your floor system was vibrating that way, you would never feel it. It'd be damped out too quickly, too small of an amplitude.
Okay, so yeah, get up to this point. We now know what vibrations are. We have our design guide. We know how to design for them, whether that's software, looking at an individual beam with our stiffness and our mass. We kind of understand there's different levels of acceptance, and kind of understand that most people aren't going to feel these vibrations, but some still will.
Yeah, no matter what, there might be someone that still feels the vibration. The AASC YouTube video that I had watched earlier, they talked about, an office building that they calculated an acceleration of under 0.5%, a natural frequency of something like 6%, and all the occupants complained. They went in, this was an office building. They went in, the guy said he couldn't even feel anything, but if their job is to stiffen it, sure they will. And they upped that, or rather reduced the gravity percentage, and they increased the stiffness, and people didn't feel it then, but it was well within the reasonable bounds of design. Any engineer seeing those numbers would say, yeah, this is perfectly fine, and yet it wasn't.
Okay, so that brings up a great point. So we know how to design for it. How do we retrofit for it?
Yeah, so again, this is back to that stiffness and mass, which is, the formula for your natural frequency. You can add stiffness to a beam, or you can add mass to the beam. I've seen stairs designed so that weights can be attached in the future. So they predict that maybe there might be some vibration issues, and have little shear tabs that come down, and you can just bolt weights right on there, which will slow down your frequency. On the other hand, fixing a beam, providing fixities at the end, or changing the bearing condition. From damping, you could put pads under. I've seen in a building bar joists sitting on pads, and the pads dissipated the energy as the bar joist moved. So increasing damping is another great way to reduce your vibrations.
Is there any systems out there that are created for retrofitting?
Man, you bet there is. There's all sorts. Yeah, so a mass tuned damper is probably the most popular system or style of system, and this is simplified as just a weight on a spring. And so when the weight bounces up and down, you want to match the frequency of the thing that's bouncing. So let's say we're looking at a single beam again. As that beam bounces up, the weight on a spring stays put more or less, and they counteract against each other. So the spring pulls the beam back down at the same time it pulls the weight back up, and they bounce against each other, fighting the movement.
That would be a practical solution to retrofitting versus maybe, let's say, a wide flange beam needs to be retrofitted for this issue. In my mind, you'd want to throw maybe a WT, maybe some more steel on the bottom flange, stiffen it up. Would you see it being work equally as well doing something like that with the mass and the spring?
Yeah, the mass tune damper, the issue with it is that it really works best with single mode issues. So I was looking at it on a bridge, and this bridge just had, problems in one mode, and it's relatively simple structure compared to compared to a building, which vibrates in a lot of different modes. So that's really the best time to use a mass tune damper. A staircase, again, same thing as a bridge, pretty much one mode.
Or a skyscraper.
Skyscraper.
Whole different.
Totally different animal.
Same idea.
Same idea. Yeah, this cantilevered column that happens to be a giant building, and a mass tune damper is a great way to take care of that, single mode. And I'm sure those things are all tuned for the first mode of vibration. If you're looking at a building, the easiest thing probably is just to stiffen up the beam. If you have access to the bottom of them, exactly, welding on a WT, and definitely welding is what I've heard. You just cannot get the stiffness bolting or screwing something on. To increase the stiffness, you need zero movement. And a bolted connection is just going to have way too much. Welding plate on or WTs on the bottom.
Well, I think that's a good little chat. The thing I want to jump into next is our talking a little bit into what we, or mostly you, designed and built to kind of replicate and show this vibration
in a
very simple...
This is our single beam. This is our representative floor. Very flexible. But to represent floor vibrations, we're working on this demonstration, and it's just a aluminum beam that spans these supports. It's about 3 feet across, very flexible, and then we have a spinning weight on this, so we can change the velocity of the spinning weight to induce a frequency into this beam, kind of show the reactions.
And we showed one of our friends the other night this and had him kind of talk through it, and we went through this, and we'll also have some videos on our website, YouTube channel, etc., showing these different levels and frequencies going through this with the strobe light, and kind of all of a sudden you can see everything lining up and matching, and it's a fairly cool system that really, I think, shows you what's going on.
Yeah, I think it gives you good perspective on how this really works, like on simple terms. Let's go to that. How would you describe what's going on here?
There's a weight in the center of that, and a motor is propelling the weight to have someone to kind of counterbalance, which is causing that rod of some sort to vibrate.
Yeah, we got a rod going across two supports, and this offset weight is swinging around so the thing moves up and down. Right now it's moving at an amplitude of 1/8 of an inch, so pretty small. It's moving pretty slowly, right, I guess.
Yeah.
All right, now I'm going to adjust it 1 second.
No way. Oh, jeez.
How much faster is it moving? The spinning weight, how much, what does it look like?
Faster is the weight?
Yeah, from what it looked like before, spinning around at a handful of revolutions.
It looks like at least twice as fast.
Twice as fast.
But the rod is moving a lot more than 1/8 of an inch, probably more like 1/4 to 1/2.
Yeah, we're up to 1/2 an inch.
Yeah.
Let's see if I can get a little higher.
Crank that sucker up.
All right.
Just kidding.
Well, hold on 1 second. So this is I think as high as it's gonna get, right? This is
okay.
A heavy 1/2 inch, maybe a little more than 1/2 inch.
Yeah.
What do you think is gonna happen if I crank this sucker up?
It's gonna separate from the.
Okay, besides this breaking.
For sure.
It's going to the moon.
It's going off. We were just talking about rockets, so. Oh, interesting.
It stops vibrating, right? Like, amplitude's back to 1/8 of an inch. So as I slow down, still, maybe that was double what it was. We're still looking at nothing.
So the higher RPMs, right?
Yeah.
Is that correct? The higher RPMs, the smoother, essentially, it is, or no?
Sort of.
think about hitting rumble strips at 200 miles an hour. And then hitting rumble
that's
strips
perfect.
at a mile an hour. Doosh, doosh,
Yeah.
doosh.
Right.
Right?
Yeah,
It's like a buggy in the desert. You ever seen the buggy suspension
Oh,
in the
yeah.
desert?
it just eats up
Yeah.
the bumps.
Yeah.
Yep.
Versus Ferrari out there.
Hey, okay, we're in the 101 class, Joe.
6th grade level here, guys.
Yeah.
6th grade level.
7 years old, okay.
So I mean, I think like this to me feels like 4 times where we started, and then going to like that half speed, and it starts to go wild again.
Oh, wow.
And then
Yeah.
if we can bring it back down, nothing. So there's something in the middle, and it's only in the middle where it just starts to freak out.
So what you're saying is in between the middle, the slower rotations don't super have an effect.
Yeah,
The end,
super fast rotations.
super fast rotations, and somewhere in the middle is it causing it to really fluctuate around the fat half-inch variance between up and down.
Yeah.
Now, something that we experimented with the other day is Max downloaded a strobe light on his phone, and you can set the hertz on there. And we matched it up exactly with it so that the weight that's rotating stayed in one spot. So every time it flashed in the same spot that when that weight came around. And so the video, I have a video of it. It's super cool.
Something I think is super cool. So this is vibrating at a certain frequency, right? It's not super fast. You can see it. And we found like this frequency is 9.4 hertz. So 9.4 times it goes up and down in a second. Almost counting. It's not super quick.
Uh-huh.
And so if this was completely off, if I give it a spring, it's the exact same frequency, right? Like if you just give it a flick, the frequency that it wants to go to, just its natural state, is 9.4, where it like
Interesting.
sits nicely. So if you force it, so this rotating weight is like forcing a frequency into this,
Uh-huh.
and as this bounces up and down, that is forcing an acceleration. When it hits that 9.4, when this is spinning at 9.4 rotations a second, this thing starts to go nuts, right? That's that. It's called natural frequency. I've been kind of dodging the word, but so the natural frequency of this condition. So it's this material, these dimensions, this span, just happens to fall at 9.4. So like when you match it, it goes crazy. When you're under, nothing really happens. When you're over, nothing really happens. So that's why this looking at a floor system where the vibrations can vary, all over the place.
Uh-huh.
Really hard to keep this kind of thing in mind. Like you don't always know,
Right.
So, Joe, what do you think
So-
on a floor system you would do to mitigate that issue?
Yeah,
in
that's what I was
design?
trying to think of. Like, how would you use that? Is
Well, this
essentially
right
what you're-
here, more of
That's right, you don't
just
use running.
Right, right.
concept.
That's just proven concept. I don't know how you would use something like that. Like, how would you
Like, use the
resolve an
information.
issue?
Yeah.
I guess the question for me that I have for you guys is what then causes that joist to flap or ripple? What is causing that
Yeah,
issue?
What's the spinning weight in real life here?
What's exciting that joist to do that?
Yes, yeah,
Yeah.
that's a better way to say it.
You and me, a lot of the time.
Just walking on it?
Yeah,
Just
so
walking
like
on it.
this is 9.4 hertz. If I go and walk across the floor, like the amount of steps I take in a second, one Mississippi is pretty much 2. It's 2 to 3 is what a person does. So if you accidentally get a floor system that's in that 2 to 3 hertz natural frequency, you'll quickly build amplitude. You'll get the fat quarter or fat half inch. That's a really, really soft floor. That's hard to hit. But like that's exactly what it is. We were reading this thing and it was like they kept mentioning aerobic studios, which is like a ridiculous thing to focus on.
Yeah.
But people are jumping to music at 4 hertz or something, or like stomping and running in place. And 4 hertz is pushing like what a floor system could be. Like a steel concrete floor system is about 3 to 8 hertz in their natural frequation. So you get people stomping or whatever,
Yeah.
and they can hit that really fast. So it'll
And
start
so
dancing.
let's say that's one tenant. Well, that can start transferring all around the building to other tenants. They're maybe sitting at their desk working, and their floor kind of shaky.
Yeah.
Our office, a big truck drives by, and that comes through the building, and you can feel the floor vibrate from a big semi truck. So there's more than just people.
Yeah,
Majority of
yeah.
the time, it's an
People,
influence of a person. I mean, I guess
Equipment,
yeah. So big
cars
mechanical
driving by.
equipment on a roof.
which would be more like this, where the fan is just
Yeah,
slightly
yeah,
off.
yeah. Exactly.
Yeah.
Yeah, it's ticking. And the ripple effect that would cause.
Yeah.
So the way we solve these issues is adding more mass to the system and then stiffening up the elements. So
Yeah,
make bigger beams, deeper beams, or adding, let's say for like the concrete and steel scenario, deeper beams and thicker concrete.
More of a overbuilt.
For service code reasons, yes, it would be overbuilt, but for this vibration issue, which is a huge, lots of lawsuits come out of this. At that point, no.
Friction is the other one that's super important. So, like, big open spans have a lot of vibration issues because there's nothing like attached to anything.
Mm-hmm.
But a house that has a lot of walls, those walls when they move, kind of rub on the ceiling and rub on the floor and dissipate all that energy just in friction. So it can be really hard to get to that resonant state, especially because most of the vibration stuff is not like the spinning wheel where people are marching and it just keeps going on and on and on. It's like a couple impulses, and you can start to excite something. So if you can dampen that quickly, nothing happens. So I'm gonna clamp this on, see if it can make it mellow out.
Yeah. So the military does not march in step over bridges.
Oh yeah, that's
for this exact reason. They don't want to hit the natural frequency of the bridge and collapse it.
Really?
So when the military marches, they'll march in sync until they hit a bridge, and then they won't.
Interesting.
Yeah.
All right.
Because of the amount of people that are doing the same thing at the same time and causing that fluctuation to ripple to the extent of collapsing.
Yeah, have you ever seen the galloping gurney thing? This is like kind of overdone in engineering school.
Yeah,
like they show you in every day class.
The eddies and stuff with the wind and everything that was going on hit the natural frequency of the bridge, and the whole deck goes like this.
Whoa.
And it's pretty wild.
Wow.
That's like the most overstated, or most accentuated idea of what we're trying to talk about.
And the wind actually wasn't even that quick. Like this eddy current thing is like when you look at a flag in the wind and it just whips back and forth like whoosh, whoosh, and changes directions. That's like, the wind hits it and it builds a pressure on one side and it sort of rolls off. So you like kind of see this stuff. It's like, water going around a rapid, except it alternates back and forth. That 4 to 8 hertz is when it's excited by wind. So like a very slow wind speed, 25 miles an hour or something, will just start to oscillate these wind currents and the flagpole just start rocking back and forth. And find out what the natural frequency of that system is. Multiple natural frequencies or modes. So fast, and you could do it with a bridge. But
this is a huge bridge.
So what is that bridge made of? Is that concrete that's flowing like that?
Yeah, that's a concrete deck.
Yep.
And that's not crumbling? So there's rebar obviously probably going through that, or no? Not in the 1940s.
There's rebar. Oh man.
That's crazy.
You'll see it collapse here fairly soon, I believe.
A car and a dog died.
You say a car and a dog died?
Yes, but no people.
Now there's a very stout bridge. Very.
Tacoma, they don't talk about that.
Yeah.
No.
Yeah, for like our system here, if you wanted to counteract that, like to make it look like the high frequency one, even when it was not in the high frequency state, you could put a spring on a weight on there that has the same frequency as that's natural frequency. So as that thing leaps up, the weight stays put, and then they sort of start to counteract each other.
Right.
So
right.
The mass of the weight on a spring wants to stay in place. The bar jumps up, and so now it's yanking on that spring. So it wants to pull it back down, and then they start counteracting each other. Now the weight wants to come up while the bar wants to come down. We can just tune that weight on a spring to be that exact frequency. So since you're not dealing with like a total spectrum here, if let's just say this is 10, like if we knew a floor system had a frequency of 10 hertz, you could build some little contraption weight on a spring that also has a natural frequency of 10 hertz, and these would just balance each other out.
Gotcha.
So that's what like really tall buildings, when they have either for earthquake effects or even just wind, they're swaying back and forth. Have you ever seen them with like the pendulums in them? Yeah. So like
Taipei Tower has got a big.
Yeah. So like it has the same frequency, so it's much shorter, building is pretty stiff relative to a pendulum. So as that thing swings, the pendulum swings the other way and basically pulls the building back to where it started.
That's sweet.
So thanks for joining us this week. Like we said, all the information about our kind of floor vibration setup will be written up in the show notes. We'll have all the pieces and parts in there for you to do this yourself.
Yeah, thanks for joining us this week. Like usual, you can check out our website, Facebook, Instagram, and whatnot. We're there.
Awesome. All right, you guys have a good one.